Professor Konstantinos Vayenas from University of Patras yesterday gave an exciting talk that stimulated a long discussion among all participants and guests of our conference, 18thLomonosov Conference on Elementary Particle Physics. Professor develops a new approach to understanding of fundamental laws of matter, of universe. Instead of the known four fundamental forces that are electric, electromagnetic, weak, strong, and gravitational forces, Professor deals only with two of them, electromagnetic and gravitational, and manage, as he claimed yesterday, and in a series of his published papers in the review journals, by the way, that it is quite enough to use electromagnetism and gravitation forces and to explain all phenomena that can be observed in high energy physics and particle physics. Would you please say just describe your the kernel thought of your approach first, and then I have two questions more. Okay.
Right. Our approach is based only on special relativity and Newton's gravitational law. In Newton's gravitational law, we are using the gravitational mass of the particles instead of the rest mass, as is commonly done. And as a result, we find gravitational attraction between particles can be much stronger than anticipated by neglecting this term. And therefore, we find that for neutrinos with energies above 130 MeV, their attraction is stronger than the electrostatic attraction between positron and electron. So this relativistic gravitational force has all the characteristics of the so-called strong force. And by using this in a very simple Bohr-type model, which also accounts for the old quantum mechanics via the de Broglie equation, we find within 1% the masses of hadrons, and also of two at least bosons, the Z and the W boson. So we have not developed any new theory. It's just a model which combines the equations of Newton, Einstein, and de Broglie, nothing else. The advantage over the standard model, if I dare say so, is that we have no adjustable parameters. The results are the same. But we can predict a few things which the standard model cannot predict.
But my impression, is, what I recall from your presentation, is that, for instance, you can mimic bosons of the standard model as the bound states of fundamental particles that are electron, positron, neutrino, and antineutrino. Is it true?
Absolutely. The W boson is just a rotating electron-neutrino pair. By doing the calculation, which is very simple, a few lines, you compute 81 GeV for the mass of the W boson. By modeling the Z boson as a trio, positron, electron, neutrino, you compute 91 GeV within 1% of the experimental value.
Well, you see, we have several presentations in the program of Lomonosov conference devoted to the problem of anomalous magnetic moments of charged leptons, G-2, of leptons and muons. And as we know, the studies, theoretical and experimental studies of G-2, of muon and electron, provide a very steady basis for checking the validity of the normal or the ordinary common theoretical framework. And when you consider bosons like W or D bosons as a compound particles, I just recall from my previous experience of many years ago when I calculated contributions to G-2 from different bosons, including the composite bosons. There can be some additional terms. And for instance, what about the G-2 within your approach? Will you see some deviation from the standard model prediction for G-2?
We have not done this.
But you should do this.
We should do, absolutely, absolutely. And what I would like to add is that we can we can describe some experiments which are easy to do and which would check the validity of our models for the bosons. The production of Z boson, which was just described by this excellent presentation from China, is to use an electron-positron accelerator to produce the Z boson. According to our model, there is a neutrino also participating in this trio. So the prediction is that if we add a neutrino, we should see an important enhancement in the rate. So this is something which can be checked very easily. Also, yesterday we discussed that if we take the jets produced in proton-proton collision and we could somehow experimentally add electrons or positrons to them, we expect again to see a very large enhancement in the rate of hadronization. So both experiments are relatively easy to make, particularly the first one, and that's why we would very much like to talk with our colleagues in China and see if this is something which could be done easily in their facility.
Well, I just thinking during your replies. Well, really, it's amusing, and I think it's, even though it will be not true, your theory, it is interesting to examine it. And one of the possibilities to consider your bound states, like Z boson, W bosons, under the very strong pressure of external environment. For instance, consider your composed bosons and put a laser beam, and you can destroy it,
sure.
and you can just produce neutrinos. Yeah, but you should calculate the rate of production of neutrinos when you just split the bound state, which are the W bosons.
Sure, absolutely. Our models are based on the decay products. In the books, you see that Z boson decomposes to positron, electron, neutrino. Therefore, we have chosen these are the components. For the W, it's the electron or positron and the neutrino. Therefore, this gave us the idea to model it so simply as a positron, neutrino, or electron, neutrino particle. Nothing really changes regarding the nature of bosons, whereas in the standard view we have so far about bosons, we consider them as mediators, as catalysts for reactions.
But the point-like particles, structureless particles.
Sure, sure, but...
There's no trivial magnetic moment, by the way.
Yeah, sure, but now they just become reaction intermediates in the weak interaction. The radius we predict is 10 to the minus 18 meters, 3 orders of magnitude smaller than femtometers, smaller than protons and neutrons. So this is another prediction, that they do have a size which is on the order of 10 to the minus 18 meters.
So my proposal and suggestions to you, you should think about a set of new experiments that in practice, in principle, might help to distinguish prediction of your model in respect to the prediction of the normal standard model theory. So you should try to find effects that will show the new effects that you can reproduce.
Sure, and it would be wonderful if we could somehow interact and collaborate in this area. Due to your very broad knowledge of electromagnetic interactions involving neutrinos, that could be a very good area to collaborate. Finally, I would like to say that we are on very solid ground. Anyone who criticizes our model is not criticizing us. We just put things together. He's criticizing Einstein or Newton or de Broglie. It's very simple. It's like the Bohr model. No assumptions, no new theory.
No, during your presentation, I mentioned that you put the names of Janes around you just to protect the model. This is also good, a good approach, you see. But nevertheless, you should think about
sure.
the proposal for new experiments, because the physics, I am a theorist, physics is an experimental science, we know.
Sure.
Only the experiment will show who is right and who is not right. So in any case, it is a great pleasure for us that you are here and presenting this very exciting presentation, and also it stimulates a lot of discussions, and I hope that in the future we will be able to continue these discussions.
Absolutely.
And you will not probably prove, but you propose an experiment And for many years, people will climb to reach the sensitivity to see your effect, because your effects, I suppose, will be very, very small in respect to the prediction of the standard model. I mean, it will be very hard to verify in the experiments. So you have a good position. So you can propose an experiment that will be realized in, let's say, in 20, 30, or maybe 100 years from now. And you have a lot of time to make new researchers in this field, you see. So
Sure, but by the way, we're certain about our calculations because it would be an enormous coincidence if we could predict the mass of hadrons and bosons.
It's surprising how sensitive your predictions are for many of fundamental properties of particles. It's surprising.
Yeah.
Really.
And let me tell something. I was trained as a physical chemist. It's only during the last 20 years that I'm in physics. I'm very excited with this. But when I was a physical chemist, we found a new phenomenon involving the use of electrochemistry to activate catalysis. The first people to reproduce, now it's in all the electrochemist and catalyst books, were also colleagues from Russia, from Novosibirsk, Professor Sobyanin and Belyaev. So I think this is a very nice coincidence that we may start also a collaboration in different and very exciting area. And I want to thank you very much. It's a great pleasure to be here. And as you say, for me it would be exciting to continue our discussions both here and in Patras or Olympia, which is nearby.
Okay, well, thank you very much.
Thank you.